Hello everyone, I am Zhenji Cao from Jing'an branch of Shanghai Open University. It is my great honor and privilege to present our latest research on personalized teaching feedback, generation based on multi-agent retrieval, augmented large language models as artificial intelligence becomes deeply integrated into education. One question grows increasingly urgent. How can we enable AI systems to genuinely understand each learner's cognitive state and deliver precise, personalized teaching feedback at scale? This is the central question our research addresses. Allow me to begin with a context. Personalized teaching feedback has long been recognized as a cornerstone of effective learning. Educational psychology research has consistently demonstrated that timely, precise, and cognitively matched feedback is a key driver of deep learning and knowledge transfer. However, in adult higher education, particularly in software engineering programs, this ideal confronts a structural dilemma. On one hand, teaching resources are inherently limited. No instructor can provide high-frequency, individualized guidance to every learner. On the other hand, adult learners exhibit extreme heterogeneity. The same classroom may contain working professionals with years of engineering experience alongside complete beginners, changing careers. Their prior knowledge varies dramatically, their learning time is fragmented, and their professional backgrounds are diverse. Any one-size-fits-all feedback template inevitably fails one group or the other. The emergence of large language models such as GPT-4 offers new possibilities, yet directly applying LLMs to feedback generation faces two fundamental limitations that remain inadequately addressed. First, the lack of learner state awareness. Conventional LLMs rely on static training data and cannot perceive a learner's dynamically evolving knowledge state. The feedback they produce tends to be generic standard answer explanations rather than precise diagnoses of specific cognitive gaps. A student who has mastered recursion but struggles with dynamic programming receives the same generic feedback as one who has not yet grasped basic function calls. Second, and more critically, severe hallucination. In knowledge-intensive domains such as software engineering, systematic evaluation reveals a troubling statistic. 37% of LLM-generated programming feedback contains errors, incorrect line, number, identification, flawed explanations, or outright fabrications. In AD's plan, where technical accuracy is paramount, erroneous feedback does not merely fail to help, it actively reinforces learners' misconceptions. Existing approaches have tackled these problems only in isolation. Some rely on single LLMs without learner modeling. Others incorporate retrieval augmentation, while neglecting the personalization driven by knowledge tracing. What remains missing is a unified framework that simultaneously guarantees technical reliability and cognitive adaptability. To bridge this gap, we propose MARAGKTPF, to our knowledge, the first system to deeply integrate multi-agent collaborative architecture, retrieval augmented generation, knowledge tracing, and personalized feedback generation within a unified framework, specifically designed for adult higher education in software engineering. Our design philosophy rests on two core observations. First, personalized feedback generation is inherently a multi-stage reasoning task, spanning learner state perception, domain knowledge retrieval, personalized strategy formulation, and natural language generation, and a single LLM cannot maintain precision uniformly across all these cognitive layers. Second, educational scenario iOS impose strict requirements for and auditability. A multi-agent architecture renders each stage decisions explicit and traceable, naturally supporting inspection and intervention. The system comprises 4 specialized agents, coordinated through a shared state bus, under an orchestrator worker protocol. The planning agent serves as the meta controller. Upon receiving a learner submission, it parses the task type, code debugging, conceptual understanding, or algorithm design decomposes feedback generation into an ordered subtask sequence, maintains the global execution state, and triggers rescheduling when anomalies occur, thereby ensuring system robustness. The retrieval agent is responsible for precise lie, acquiring reference materials from the software, engineering knowledge base. It employs a hybrid strategy combining face-dense vector retrieval with BM25 sparse retrieval to exploit their complementary strengths. Dense retrieval captures semantic equivalence, recognizing that my loop 1 terminate and loop termination condition error refer to the same underlying concept, while sparse retrieval excels at exact matching of API names and algorithm identifiers. Critically, we integrate a Krag-style quality evaluator that assigns 3-level confidence scores to retrieval results, automatically triggering query rewriting or expanded retrieval when confidence is insufficient, thus blocking, at the source, hallucinations caused by retrieval failures. The personalization agent constitutes the core module enabling differentiated feedback. It maintains and updates each learner's dynamic knowledge state through a 3-layer fusion mechanism. The sequence encoding layer employs SAKT, self-attentive knowledge tracing, to identify which historical exercises are most relevant to the current knowledge point. The semantic enhancement layer leverages GPT 402 extract question semantic vectors, bridging behavioral data and content understanding. The forgetting modeling layer introduces exponential decay factors over time intervals, specifically adapted to adult learners. Fragmented learning rhythms. Together, these layers produce an 8-7-dimensional knowledge mastery vector, accompanied by an error pattern matrix distinguishing conceptual, syntactic, logical, and boundary condition errors, capturing not merely whether a learner knows something, but how well, in what context, and with what retention probability. The feedback agent receives the retrieval, context, and personalization parameters, then generates structured teaching feedback through carefully engineered prompts. What distinguishes our approach is the generation, evaluation, regeneration, or GERG cycle. After initial draft generation, the agent conducts a 4-dimensional self-review covering error localization accuracy, cognitive level matching, suggestion, actionability, and linguistic conciseness. Any dimension falling below threshold triggers regeneration, with specific revision instructions for up to 2 refinement rounds. This mechanism raises the proportion of effective feedback components from 27.72% to 98.49% to rigorously evaluate the system. We conducted a 6-month longitudinal controlled experiment in the software engineering program of an adult higher education institution. We recruited 200 working adult learners, mean age 28.3 years, with work experience ranging from 0 to 12 years. Random lie assigned to experimental and control groups over 6 months. The system logged approximately 15,000 exercise interactions spanning 4 course modules, data structures, algorithm design, object-oriented programming, and software engineering practice. To precise lie isolate each technical component's contribution. We established 4 baseline systems. Direct LLM, representing the most common LLM educational paradigm. Single rec, isolating the independent contribution of retrieval augmentation. MAS NORAG, evaluating the incremental value of multi-agent collaboration over RAG. And MOSNOCT, quantifying knowledge tracing S, contribution to personalization. Our evaluation framework spans 3 dimensions. Automated metrics including Bertskarev 1, RAGAS, faithfulness and answer relevancy, and GEVAL coherence. Pedagogical metrics including feedback specificity, helpfulness, validity, and technical hallucination rate. And learning outcome metrics, 6-month course, test score improvement, and learner satisfaction. The results demonstrate that MARAGKTPF significantly outperforms all baselines across every evaluation dimension. with all differences statistically significant at p0.001. Most strikingly, the technical hallucination rate falls to 3.8%. A 79% reduction from direct LLMS 3%. This two-stage reduction pattern is instructive. Moving from direct LLM to single RAG achieves a 47% reduction, demonstrating the foundational value of external knowledge grounding. The further reduction to 3.8% is attributable to RAG quality control, confirming that hallucination suppression must address both whether to retrieve and the quality of what is retrieved. Feedback specificity reaches 0.841, enabling highly precise diagnosis rather than generic advice such as check your boundary conditions. The system generates feedback of this kind. You used asterisk less than operator in the loop termination condition at line 23, which aligns with your recurring boundary omission pattern in the linked list traversal module, where your current mastery level is 0.62. The learning outcome effect size reaches Cohen SD equals 0.79, a medium to large effect. In practical terms, the experimental group average performance exceeded that of approximately 78% of control group learners. This demonstrates that improvements in feedback personalization carry substantive educational value, not merely enhanced subjective satisfaction. The ablation experiments further reveal differentiated and complementary contribution mechanisms. RAG contributes most significantly to hallucination suppression, exhibiting a clear dose-response relationship. Knowledge tracing contributes most prominently to feedback relevance. The gap between MAS, no KT, and the full system on RAGAS answer relevancy 0.812 versus 0.871 represents the largest single component gain across all ablation comparisons. Its core value lies not in improving linguistic quality, but in transforming feedback from technically correct yet cognitively misaligned to precise lie matched to the learner's current knowledge state. Multi-agent iterative refinement independent lie enhances linguistic coherence. Even without external knowledge support, MAS no RAG outperforms single RAG on G-eval coherence, demonstrating that the GERG cycle improves feedback, language quality, independent lie of retrieval. Post-experiment surveys, with an 87% response rate, reveal three noteworthy patterns. First, personalization perception correlates significantly with learning. Motivation Pearson R 等于 0.67. 87% of respondents felt the feedback was clearly targeted at me personally. Second, knowledge, tracing, transparency significantly affects trust. When feedback explicitly presents knowledge mastery states, trust scores rise from 3.8 to 4.51 on a 5-point scale. Third, the system shows limitations in handling cross-knowledge point compound errors. 23% of respondents reported difficulty distinguishing primary from secondary error, priorities which point directly to our future improvement direction. In conclusion, MARAK TPF is, to our knowledge, the first unified framework deeply integrating multi-agent collaboration, retrieval augmented generation, knowledge tracing, and personalized feedback generation. ASX. Month-long UDNL experiment with 200 adult learners demonstrates significant improvements in hallucination suppression, feedback specificity, and learning outcomes providing are producible. Technical paradigm and empirical evidence for the architect-Euro design of intelligent educational systems. Looking ahead, we identify three promising directions: LLM-driven adaptive knowledge, ontology construction, automatically extracting knowledge points and their dependencies from course materials, multimodal feedback generation, integrating code execution traces, memory state diagrams, and algorithm visualizations, and long-term cross-semester learning tracking, combining spaced repetition with forgetting curve modeling. Thank you for your attention.